more video on memories for digital circuit design. So of course, as we discussed in the previous video, so memories can be basically classified into two major categories. One is read-only memory and the other category is read-write memory. So coming to of course classification of read-write memories, we can just we can say it as it's a volatile memory and non-volatile read-write memories. So in this volatile read-write memories, so the way how you access the data, that depends on whether you can able to randomly access the data or whether you have to serially or sequentially access the data. So there are again two categories. If we can able to access the data randomly from whichever location it is placed, so it is called as random access memory. Again, in that we have got two different categories, that is SRAM and DRAM. So where SRAM is one, okay, where you can where the data will be stored forever as long as the power is there. Of course, it is static RAM. The data will be stable as long as the power is there. Coming to dynamic RAM. Even in this case, you can able to read-write the memories, but as long as the power is on, it is not guaranteed that whatever data that you have stored will going to stay there, because there is no feedback loop available for the data to be retrieved by itself. So in this case of DRAMs, we may have to just keep on refreshing the data that need to be stored every time or very often. Coming to a read-write memory which is non-randomly accessible, FIFO and LIFO, that is last in first out and first in last out, and of course shift register type of memories, and then this these type of memories, okay, where we have this CAM, which stands for contents addressable memories. So these are, of course, you can able to address a particular content which is specifically, you can just go on to it. This is content addressable memories. Of course, these are all non-random access. You cannot access the data wherever you are. Suppose if you are there in a particular position, you can able to access the content and you can able to retrieve the values. Of course, you can able to rewrite. Coming to non-volatile read-write memories, you can see now this is again it is called as ROM, but we say this as this is read-write memory, because even though it is read-only memory, since you can able to program it and you can able to erase it, so that's why it is coming under the category of non-volatile read-write memories. Even though it is ROM, it is, you can able to write upon taking out the memory and then erasing it using UV light. And of course, there is an improved version of the same ROM which you can still say it as read-write memory. Now you can able to erase the program whenever you want electrically and then reprogram it. And of course, flash is one more type of such memories where you can able to read-write the memories very often. And there are some memories where you may have to store the data only once forever, so that are coming under this mask programmable ROMs, read-only memories. So these are all very specific codes where for a particular system that code needs to be there for the entire its lifetime. So such type of programs will be written in this read-only memories. All default settings will be put in this read-only memories. Coming to timings, memory timings, you can see now we know that memory is nothing but you have to read the data and write the data onto the memories. So let us try to understand what is this. Okay, read. So assume that okay, you are given a read request to read the content from your data from the memory location. So once the read request is received from an external signal, so it will just actually pass on to the memory and it will ensure that the data is ready after some time from the reception of this read request signal. Once you get the read request signal, so there will be some time required to access the data from the exact data point where exactly it is located. So this is read access time, the minimum time required for the memory to give the access to the data that is available upon getting the read request. So once the data is available, the user can able to certainly read the data which is valid because it has pointed to a particular position wherever it is located. And then before you actually do the second read operation, so the data should be read properly. So this is read cycle. So before the next read request comes, we have to ensure that the entire data is read because of the previous request. So this is how the read cycle is restricted due to one time, that is called as read access time, that is the time required for the memory to give the access to the external user to read the data. And then once the data is read, so once the data is completely read, you can go for the second read operation. So this is about the read access and read cycle. And then coming to write, because we are also supposed to write the data onto the memory. So whenever we actually want to write anything, so we have to again give a write request. So once the write request is given, and once the location of the where the data should be written, once that is specified, you can see here before my write signal goes high, so the data should be ready here. So the data should be ready here. So once the data is ready, so once the write access time is elapsed, that is once the location of the memory is fixed, so after the write request, once you locate where you are to supposed to write the data, then you can able to write the data. You can see at the end of write access, you would have written the entire data to a particular location, so of course you can able to certainly give the second write signal, so upon once the data is completely written. So this is about different timings for read write of a memory. And coming to memory architecture, so assume that you have to write n number of words. So each word can be of m bits. So assume that it's a 8-bit data. You got around 1024 words to be written onto a particular memory. You can see, of course, as I said, m bits. So these are all individual bits where you'll be storing ones and zeros. So assume that you have got 0 to n minus 1, that is totally n number of bits. And if at all, if you want to access this particular word, which is, it can be 0th word, it can be kth word, it can be 100th word, it can be 1000th word. In such case, if you want to identify, if you want to read or write to a particular word, you can see you may have to have an address. So this S0 to Sn-1. So you got n number of address lines, so that suppose you want to write to the second word, then S2 should be activated, so that you can able to access the data that is there in this word number 2. So you may have to have n number of address lines to reach out to any of the word here. So which is a very huge number. Assume that you got 1 million words, so then you may have to have 1 million address lines to locate that particular thing. So that can be slightly modified here with the use of a decoder. So here you can see, if you have 1 million words, so you may have to have 1 million addresses. It's like having, you have a street with 100 house. If you want to go to a particular house, so you have to know the address of each and every house. So that's what a person should know, the addresses of all 100 houses. But whereas when it comes to a decoder, so here you can see, even though you have same number of n number of words, so these are again in order to reach out to each of the word, we need to have an address line. But the actual address that is required to access a particular word can be drastically reduced if you use a decoder. So decoder is one where it decodes. Suppose if you have n number of inputs here, if you have n number of inputs, the number of outputs of the decoder is 2 power n, meaning if you have only 3 lines here, if you have A0, A1, A2, if you have only 3 lines, I can have A0 to A7. That is, there can be 8 possible address lines, distinct address lines, because of three binary addresses. So it happens so that if it is 000, you'll be referring to S0. If it is 111, you are referring to S7. Likewise, the number of address lines required to access these number of bits will be drastically reduced with the usage of this decoder. So this decoder decodes the given address and it locates to the desired particular word location which you are looking for. If you are looking for a particular word, so you may have to just write the corresponding input decoded address so that you can able to access that particular bit. Okay, now assume that, okay, let us just go back and try to see uh, if you want to access. Let me just go here and then assume that you got around 1 million. You got around 1 million words. So assume that each word has got 8 bits. Each word has got around 8 bits. So in order to address these 1 million, so usually the number of words in a memory will be always 2 to the power of n. 2 to the power of n. It will be always 2 to the power of n. It can be, you can have only one address line. You can have only one memory word. You can have 2. You can have 4. You can have 8. You can have 16. So in between that, it is not recommended because the address lines will be always n in number. Always n in number. That is encoded address now. Suppose that you got around 1 million words. So instead of seeing it as 1 million words, so you can write it as 2 to the power of 20. 2 to the power of 20 happens to be 1,048,048,000. So it happened. Let me just try to find out, okay, how much will be the number. Suppose if you do 2 to the power of, sorry, 2 to the power of 20, it is 1,048,576. So these are the number of words that you can able to address. So that you can start with zeros and you can go up to 10 lakh 48,575. So including zero, you got these many. So you can see here, you need to have those many address lines if you have it, if you are don't using it, if you are not using a decoder. If you're not using a decoder, you can see now. So this is 8-bit wide. This is 8-bit wide because we are looking at the bits of one word. One word is of 8-bit. One word is of 8-bit. But you can see on the vertical you have 10,48,576 locations, but on the the vertical, on the horizontal you have those many lines, but vertical you have only 8 bits. Only 8 bits. The aspect ratio is very poor. So this lengthwise it is, the height wise it is so big, but the width is so small. The width is so small. Yes, 18th. Okay, this is what we have. So the aspect ratio is very poor. Okay, this is one thing. Okay, you don't have a very good aspect ratio because the height is so high but the width is so small. If I use a decoder, I can have only 20 address lines. I can have 0 to 19. So with only 20 address lines, I can able to access these many number of words. But the problem is the aspect ratio. We know that the width is only 8 bits, but you can see that the number of words are so huge. So if you find the aspect ratio of this one, the aspect ratio of this comes out to be, so it is now 1,048,576 divided by 8. So it is 131,072. So this is the aspect ratio, which is very poor. We are looking for an aspect ratio of somewhere around 1 or close to 2. So we are not supposed to have aspect ratio very large. So you can see the aspect ratio is so big that because we have this restriction, we have only 8-bit word, and then we got these number of, this is for only 1 million. This is for 1 million bits, so 1 million bytes. So 1 million bytes. Okay, why it is called as bytes is because each word is of 8 bit and that corresponds to bytes. So let us see in the next video how do we able to reduce the aspect ratio of these type of memories. Of course, this decoder will certainly reduce the number of address lines, but this way is not reducing my aspect ratio. You can see you got on vertical these many number of rows, but on the these many number of rows are there. The number of columns are only 8. So since the number of rows are very high, number of columns are very less, the aspect ratio is too high, which is not good to have a memory with such a huge aspect ratio. We always look for a square a square memory where you have the rows, the number of rows and number of columns are almost equal, so that aspect ratio is close to 1.